Okay, so let's start our discussion by recalling something from the second section. In the second section, we came across this theorem 622. So basically what it says is that if T is a linear operator on a finite dimensional vector space V and lambda is a characteristic root of T. This is a characteristic root of T which is in F, then lambda is a root of the minimal polynomial of T over F, where of course F is the field on over which V is a vector space. Now it's not necessary that all the characteristic roots of T lie in F. You know that very well. You may have to extend F, and in some extension you will have all the roots. Now let us express the fact that say all the roots of the minimal polynomial of T lie in F using some kind of language. When that happens, we will say that T has all its characteristic roots in F. That is, we say that T in A of V has all its characteristic roots in F if all the roots of the minimal polynomial of T over F lie in F. That means saying that T has all its characteristic roots in F actually means this, that all the roots of the minimal polynomial of T over F lie in F. Okay, so this is something that we will use in the statement of the result that we will prove today. Now, we have seen in the previous section, the section where we studied matrices, in one of the exercises we have seen the definition of a triangular matrix. A triangular matrix is a matrix such that the entries above the main diagonal of the matrix are all 0. Actually, if the entries below the main diagonal are all 0, then such matrices are also called triangular matrices. For example, this is a triangular matrix. Say -1, 0, 1, 2, 0. This is a 3 by 3 triangular matrix where this of course is the main diagonal, the leading diagonal. All the entries above the main diagonal are 0. Now, it may happen that some entries on the diagonal may also be 0 and the entries below the main diagonal may also have 0 entry. But the entries above the main diagonal are all 0. Such matrices are called triangular, and more specifically, such matrices are called lower triangular, because all the possibly non-zero entries appear on the diagonal and below the diagonal, so lower triangular. Similarly, you also have something like this. Say this 3 by 3 matrix. Here, all the entries below the main diagonal, that is these entries, are 0. On the main diagonal and above the main diagonal, we may or may not have 0 entries. So such matrices are also triangular. More specifically, they are called upper triangular. In general, any such matrix is called a triangular matrix. Similarly, we can also define a triangular linear operator. T in the algebra A of V is called triangular if V has a basis say V is n dimensional, so that any basis will have n number of vectors, such that the effect of T on the basis vectors is triangular. In what sense, we will understand once we see the equations. Such that if you apply T on V1, then that is just a multiple of V1. If you apply T on V2, then it's a linear combination of V1 and V2. Like that it goes, and following the pattern, the image of Vi under T will be a linear combination of all the V's starting from V1 and ending at Vi. That is these. Alpha I, Vi. In other words, Vit is the linear combination of Vi and the preceding vectors of Vi in this ordered basis. And the last one, in fact, has all the vectors involved. If this happens, then we say that the operator T is triangular. Actually, you do understand what is going on here. For example, if you write the matrix of T in this basis, then that matrix will be triangular. Instead of following this pattern, you can follow the other pattern also. This one will give you a matrix that will be triangular, but what? Upper triangular or lower triangular? It will be lower triangular. So you can have a similar one where you will get an upper triangular matrix. No matter what the case is, such a linear operator T will be called a triangular operator. Okay, so let us now state our result. This is Theorem 641. V is a finite dimensional vector space. There is no need to say that again and again, because that is what we are considering. Let T be a linear operator on V, and let T have all its characteristic roots in F. If this happens, then V has a basis in which, that is with respect to which, the matrix of T is triangular. Or one can more simply say that let T be an operator having all its characteristic roots in F, then T is triangular. That's it. So that is the claim. And let us now prove this. The proof is by induction on the dimension of the space V over F, the dimension of the underlying space. Because it is finite dimensional, so we can follow this path. If this dimension is 1, if V is one dimensional, then what is the dimension of A of V? A of V is an algebra, but being an algebra, A of V is also a vector space, so it has its own dimension. That dimension is, you see, if the dimension of V is n, then the dimension of A of V is n squared. We already know this. So that means now A of V is also one dimensional, and that is why the elements of A of V are scalars. This is how the sentence is written in the text, but what is its actual meaning? The meaning is that, you see, since A of V as a vector space is one dimensional, so A of V is isomorphic to the underlying field F itself, and in that sense each operator on V now can be regarded as a scalar. And because of that, the matrix of any such operator under any basis for V is a 1 by 1 matrix. And a 1 by 1 matrix by definition is triangular. Okay, the condition for a matrix to be triangular is vacuously true for a 1 by 1 matrix, because when you have a 1 by 1 matrix, say something like this, A is its only entry, then this itself is the diagonal. So there is no entries above the main diagonal, there is no entries below the main diagonal. So the condition that either all the entries above the main diagonal be 0 is vacuously true in this case, simply because there are no such entries. And also at the same time, the condition that all the entries below the main diagonal are 0 is also true. In fact, these two conditions are simultaneously true in diagonal matrices, and this is a diagonal matrix, and that is why it is triangular. So in this case, there is in fact nothing to do, and hence the claim is true. Okay, in order for this to be more clear, you can write all the details. However, you should also learn to argue like this sometimes, because the further you go, the more involved the results and their proofs will be. So you cannot afford to write all the details all the time. This will very quickly be unmanageable. So you should get the idea in your mind that sometimes some such things need to be written where you do not exactly show all the details, you skip details, but if you are asked to provide all the details, then you will be able to do so. Okay, so with that understanding and trust, you go on writing like this. However, you should also keep in mind that you should not be careless, and especially you should not write something about which you are not sure. About these things we are sure, and we know what, for example, what this one means, that all the elements of A of V are scalars, in the sense that A of V now is isomorphic to F. That is why. So we now have a basis for our induction. The next is the induction hypothesis. Assume that the claim is true for all vector spaces over F of dimension n minus 1 for some arbitrary but fixed integer n greater than or equal to 2. We need n to be greater than or equal to 2, so that n minus 1 stays greater than or equal to 1, and that's because we have started at 1. Alright. So now the next job is to do the induction step. Say we have a vector space whose dimension is n, and say we have an operator T on that space having that property, that all its characteristic roots are lying in F. So let V be a vector space over F of dimension n, and let T belonging to A of P have all its characteristic roots in F. Next, we are going to choose one such root. Let lambda 1 belonging to F be a characteristic root of T. Alright, so what does it mean? See, by definition it means that the operator lambda 1 minus T is singular, and a consequence of that is that there will be a non-zero vector V1 on which if we apply lambda 1 minus T, we will get 0, and that in turn leads to the equation that V1 T is equal to lambda 1 V1, that thing. So we are going to next write that equation. Then there exists a vector V1 not equal to 0 in V such that V1t is equal to lambda 1 V1. Okay. So now next we consider the subspace of V spanned by this single vector V1. V1 is a non-zero vector. Actually, it does not matter. If any vector you have, it will span some subspace. So like that, V1 also spans a subspace W. The elements in W will be just scalar multiples of V1, where alpha varies over F. Now since V1 is non-zero, the singleton set consisting of V1 is the basis for this subspace, and that is why W is one-dimensional. So we just straight away write the dimension of W over F is 1. Next, you consider the quotient space of V by this subspace W, and let us call that V bar. So the elements in V bar are cosets of W by vectors coming from capital V. Now by a previous result, in fact I think I have written it here, lemma 426, because we do not remember the numbers now. Now by lemma 426, the dimension of V bar over, so this lemma is actually nothing but that one which tells us what the dimension of a quotient space is. This is dimension of V minus dimension of W, that is n minus 1, because W is one dimensional and V is n dimensional. Okay. So we are slowly nearing a situation where we will be able to apply our induction hypothesis, but we are not there quite still. Okay. Now we are going to recall the result that we proved in the previous linear algebra video, which is this result, lemma 641. Now by that lemma, it is that lemma whose proof involved that large calculation, where an operator T induces another operator T bar, that thing. Now by lemma, it's a lemma, no? Yeah. By lemma 641, T induces an operator T bar on the quotient space V bar. So T bar will belong to the algebra of operators on V bar such that and let us also recall the definition of T bar. Okay, we will need it at some point. What was T bar? How was it defined? You see, because we are defining it on V bar, which is this quotient space, so the input for T bar will be a coset of W in V. So it will look like this, V plus W, where this V is coming from capital V. If you recall, the definition of T bar was this. What you do, you apply T on V and take the corresponding coset. Okay, so that was T bar. Such that, so what we concluded is this. One conclusion of that lemma is that this t bar is actually a linear operator on p bar. And there was another conclusion, namely that the minimal polynomial for t bar divides the minimal polynomial for t, such that the minimal polynomial for t bar over f divides the one for t over f. All right. Now recall the hypothesis on T. What do we know about T? It is given that T has all its characteristic roots in F. What that really means is that all the roots of the minimal polynomial for T over F are inside F. Since all the roots of the instead of writing this in detail, we can use that language, no? Use that language, but after all we have to say in terms of minimal polynomial. Okay, since all the roots of the minimal polynomial of T over F lie in F, the same is true for the minimal polynomial of T bar over F. Actually, giving no names to these polynomials is causing these long sentences. The same is true for the minimal polynomial of T bar over F. So basically what we are saying here is this. Suppose that the minimal polynomial for T over X is Px, and the minimal polynomial for T bar over X is, say, Qx, and it's we know from this lemma that Qx divides Px. Now it is given that the roots of Px, all the roots of Px lie in F. Now because of this divisibility relation, all the roots of Qx are also roots of Px, plus maybe Px has extra roots. But then automatically all the roots of Qx also lie in F. In other words, the characteristic roots of T bar all lie in F according to that language. That is, the characteristic roots of T bar all lie in F. But I think I have already made a mistake. I forgot something. In order to be able to apply this lemma, it's not enough to simply have an operator T, but the underlying space W should be invariant under T. That part I forgot to write. Okay, so before writing this, you should also write, after writing that W is a one-dimensional space, you should write which is invariant under T. But how? How is W invariant under T? Let me show that here. What is W? Without having that invariance, you cannot apply this lemma. W is actually the set of all scalar multiples of that vector V1. Being invariant under T means what? It means that if you choose any vector from W, apply T on that vector, the result should again be in W. Let's do that for any such vector. Say we choose alpha V1 and then on that we apply T. Since T is a linear operator, so this will be equal to alpha times V1 T. But V1 is a characteristic vector of T corresponding to the characteristic value, characteristic root lambda 1. So this is lambda 1 V1 and this is equal to alpha times lambda 1 V1 using one of the axioms of vector space. And this clearly again is a multiple of V1. So this belongs to W. And that's how W is invariant under T. Okay. Fine. So all these things are okay. They are justified. So now we are in a position to apply the induction hypothesis. So what do we have now? Let us assimilate the things that we have got so far. We now have a linear operator T bar on V bar. Okay. The dimension of V bar over F is n minus 1 and all the characteristic roots of T bar lie in F. So by the induction hypothesis, what will happen? V bar will have a basis in which the matrix of T bar will be triangular. That kind of triangular which we considered here, in the discussion before the statement of this theorem. So by the induction hypothesis, there is a basis of V bar such that, let me write the equations first and then we will discuss this part, what we have written from the induction hypothesis, such that V2 bar T bar is equal to alpha 2 to V2 bar. V3 bar T bar is alpha 3 to V2 bar plus alpha 3 V3 bar. These equations may look somewhat strange and the way we have written these vectors may also look a little strange, but we are doing these things so that we ultimately can arrange the things for our final conclusion properly. That's why we have started with 2 instead of 1. and continuing like this, the general equation will look like this: alpha I1 V, oh see, yeah, 2, it will be 2, it's not 1, V2 bar plus alpha I2 I3. See, I cannot change habits so easily. We are used to writing like that, no? So naturally, after writing something here, 2 comes. Alpha I n, no, it won't be I n, it will be I, because I cannot go all the way to n. This is only I. Yes. And in the final equation, of course, we can use all the vectors. So this will be alpha n2 v2 bar plus alpha n3 v3 bar and so on plus alpha nn vn bar. Let us now come to the question of what we have written here actually. By the induction hypothesis, V bar will have a basis. How many elements will there be in the basis? N minus 1. We have started from 2 and we are ending with n. And the number of vectors here is n minus 1. Because if you started with 1, it would have been n. So there is 1 less, so n minus 1. And of course, the effect of t bar on these vectors follow the usual pattern. And here also, because we are starting from V2 bar and not V1 bar, so we have adjusted the subscripts of these coefficients. You will realize why we have taken it like this. There is one more thing. What are these things actually? These are not ordinary vectors. These are actually coming from V bar, and that's why each one of them is a coset of W in capital V. So each one of them, for example, this V2 bar really looks like this, where V2 is some vector coming from capital V. In fact, that's what we are going to write next. Again, in a language which may be confusing a little bit. Now, so this is how the author has written. Now let V2, V3, etc., Vn in V be vectors that map into V2 bar, V3 bar, etc., Vn bar respectively. What is this map into? What does it even mean? To understand this, let us go back to an idea that we discussed while discussing about vector spaces and homomorphisms. You see, say you have a vector space V. Okay, not this V, but just a vector space V. And you have a subspace W. Again, not this W, some subspace W. You remember there was a function that one can define from V into the quotient space V by W, and that function is defined like this: V phi is equal to V plus W. We proved that this function is a vector space homomorphism. or in other words a linear transformation, that is onto whose kernel is that subspace W. Okay, so it was, I think it's, if I am remembering the names correctly, this is called the first homomorphism theorem, not the first isomorphism theorem, okay, first homomorphism theorem. This tells us that this quotient is a homomorphic image of V. It is in this sense that we are saying let V2, V3, P and B vectors in V that map into these things. What that means is this, let me just continue the discussion a little bit more. That is, V2 is a vector in V for which V2 phi, which is V2 plus W, is V2 bar. V2 bar is some coset of W, right? Let that coset be given by V2. So that kind of vector V2 is. Although this homomorphism is onto, but it's not necessarily one-to-one. It is one-to-one precisely when W is the zero space. Okay. In general, it's not one-to-one. So for a single V2 bar, you may get more than one V2s. That's why we say that let this be vectors, not the vectors. Okay, some vectors for which the corresponding coset is this, and this map into is with respect to that map. Put simply, we are saying that these are some vectors in V which are giving us cosets which are these respectively. Okay. So with this understanding, we are next going to claim something which we will not prove here itself. Then, if one takes the set of these vectors and also add the vector V1, that is our original characteristic vector of T with respect to the characteristic root lambda 1. That is, if one considers this set, then this is a basis of our original space V. How? That is exercise 3. So when solving these exercises, we will see how. Right now we have to take it for granted that this becomes a basis for V. Okay. So now we go back to these equations and see what we get from these equations. For example, the first equation is this. So the author writes, since V2 bar T bar is equal to alpha 2 to V2, let us straight away do that calculation itself. Since V2 bar T bar is equal to alpha 2 to V2. Now we know what V2 bar is. V2 bar is V2 plus W, on which we have to apply T bar, and we also know the definition of T bar. That's why I was recalling the definition of T bar there. And let's see what we get. So we have, that means we are having this. Is equal to alpha 2 times V2 plus W. This is the real meaning of that equation. Now if you apply the definition of T bar, this becomes V2T plus W, and here doing the scalar multiplication, From the definition of scalar multiplication, you get this. And this in turn implies V2t minus alpha 2 V2 belongs to W. If two cosets are equal, then their representatives, if you take their difference, that belongs to W. Okay. But what is W? W consists of all the scalar multiples of V1. And so we can now write equal to some scalar multiple of V1. And we choose to write 2, 1 here times V1. For you need to write for some alpha 2, 1 belonging to F. Now if you rearrange things a little bit, you get let me write that one first. V1 plus alpha 2 to V2. Did you see that this is what we wanted for t, in the second equation? In general, if you look similarly at what? Say Vi bar t bar. In general, we have, let us also see the general calculation. So the general one is this. Vi bar t bar is equal to alpha I2 V2 bar plus alpha I3 V3 bar, like that till alpha II Vi bar. Okay, so just like that thing, here you have Vi plus W on which you will apply t bar. And on this side, on the right hand side, we have alpha I2 times V2 plus W plus alpha I3 times V3 plus W plus alpha II times Vi plus W. The left hand side is Vit plus W, and the right hand side, using both the definitions of scalar multiplication and vector addition, on the space V slash W, the quotient space, you get alpha I2 V2 plus alpha I3 V3 etc. plus alpha II Vi plus W. Do not forget to write that plus W. Both the sides are cosets of W. So this means that Vit minus this belongs to W. So just like this one, this difference is also going to be some scalar multiple of V1. So this implies Vit minus is equal to alpha I1 V1 for some scalar in F, and this implies Vit is alpha I1 V1 plus alpha I2 V2. Let me write one more since it was there, plus alpha II Vi. So we seem to have got what we wanted for V2, V3 all the way up to Vn in this form. Just for the sake of showing everything together, let me just write this. We have got this, right? Alpha II Vi. However, what about V1t? V1t, you may remember, is lambda 1 V1. Now, in place of lambda 1, you can simply write alpha 1 1 V1. You just give a new name to lambda 1, that's it. In fact, in the beginning itself, I could have called it alpha 1 1. But I forgot, okay, that it will appear like this. So we can just simply rename it. A single person can be given multiple names, usually people have. So you now see that this is what we wanted, right? So this completes the induction and proves the theorem. So in order for this theorem to be true, all the characteristic roots of T need to be inside the base field itself. Now this happens for, in particular, the field of complex numbers, because by the fundamental theorem of algebra, any polynomial with complex coefficients has at least one complex root, and using that fact and synthetic division, it turns out that all the roots of a complex polynomial are complex numbers. So if the minimal polynomial of T is a complex polynomial, in other words, if the underlying field is the field of complex numbers, then on that you have this result, that any operator will have a will be triangular. In other words, there will be a basis for the vector space in which the matrix of that operator is triangular. Okay, so that is the result. And in fact, there is a matrix version of this result as well, about which we will discuss in the next linear algebra video, next Friday. Okay, so let me just stop here itself. So see you in the next upload, which is tomorrow. Tomorrow we are going to start Riemann integration in analysis. So that's just it. So see you tomorrow. Until then, this is me, Lucifer, from a mathematical group. Have a nice day.